All right, today we're going to talk about one algebraic method for solving these systems and finding the point of intersection of the lines. One of the downfalls with the graphing is that it can be imprecise if you're not using a straight edge or something like that. It can be a little bit imprecise and cause some issues that you may not land right on the exact intersection. The other thing is with graphing is what happens if we have solutions that are fractions, which could cause issues as far as, 2/3 and 3/4 could look very similar on a graph. So the algebraic methods that we will be talking about the next 2 days are just more precise options. They give us the precise points of intersection. The first method we're going to talk about is a method called substitution. Now, a substitution, we're doing just that. We're doing substituting. And you want to use substitution whenever you have a variable that's already by itself in an equation, or we can very easily get the equation or a variable by itself in one of the equations. Now in these two, in A and B, we have variables that are already by themselves. For example, in A, we have y by itself here. Okay? So y is already by itself. So we're going to take what y is equal to and substitute that 3x in for y below. So we're going to take the 3x and substitute it in for y in the other equation. So instead of x plus y, we're going to have x plus 3x equals negative 32. And then we just solve this for x. So 4x equals negative 32. And then x is equal to negative 8. So that is the x coordinate of the point of intersection, is negative 8. And then to find the y coordinate, we can take that negative 8 and just substitute it back into that top equation, because that's the easiest one to work with. And 3 times negative 8 is negative 24. So all we did was we took that negative 8 and substituted it in, and we ended up with negative 24. So negative 8, negative 24 is our solution. Now you can always check to make sure it works. Negative 24 is equal to 3 times negative 8, and negative 8 plus negative 24 is in fact negative 32. So that is in fact the solution to the system. Now, the second one, we've got a couple of variables by themselves. So we can take this x, or the 2x plus 7, and substitute it in for y in the second equation. So then we will have 2x plus 7 equals x minus 1. So then solving this equation for x, we subtract x from both sides to get an x. And we also subtract 7 from both sides to get negative 8. So x, once again, is negative 8. That's the x coordinate of the point of intersection. And then to find the y coordinate, plug negative 8 into one of our two original equations. It doesn't matter which one. If we choose the top, y is going to be equal to 2 times negative 8 plus 7. And then we do the arithmetic. 2 times negative 8 is negative 16, plus the 7 is in fact negative 9. And again, you can check to make sure this solution is correct. Negative 9 is equal to 2 times negative 8 plus 7. Also, negative 9 is equal to negative 8 minus 1. So that is in fact the solution. Now in the next two examples, there is not a variable by itself, but if we look in the bottom equation, we can pretty easily get y by itself by adding 2x to both sides. So then y is equal to 2x minus 3. Now we have y by itself, and then we can take what y is equal to and substitute it in for y in the other equation. So instead of 3 times y, we're going to have 3 times 2x minus 3 plus 4x equals 14. I keep getting stray marks here. But now we solve this equation for x by distributing the 3 and then combining the like terms to get 10x minus 9 is equal to 14. And then we add 9 to both sides to solve this for x. So 10x is equal to 23. So then when we divide by 10, we get 2.3. So that is the x-coordinate of the point of intersection. And now you can imagine that if you were graphing this, how would we know that that x-coordinate was 2.3 and not 2.4 on the grids that we have been using? So this is one of the benefits of the algebraic methods for this. So now to find the y-coordinate, we're going to take the 2.3 and substitute it into this one. So 2 times 2.3 minus 3. So then doing the arithmetic, 2 times 2.3 is 4.6, minus 3 is 1.6. And that is the solution to the system. And again, you can always check this solution. So if we plugged it back into this top original equation, we'd have 3 times 1.6, which is 4.8, plus 9.2, which is in fact 14. And then we take negative 2 times 2.3, which is negative 4.6, plus 1.6 is in fact negative 3. So that is in fact the solution. Now for our second one, our fourth example, for part D, we can solve 4x pretty easily in the bottom equation. And I'm guessing that needs x plus 3y is equal to 7. So then x is equal to negative 3y plus 7. And then we substitute that in for x in the top equation. So 6y plus, instead of 5 times x, we'll have 5 times negative 3y plus 7 is equal to 8. So then, distributing the 5, we have 6y minus 15y plus 35 is equal to 8. And we combine the like terms on the left side, we get negative 9y. And then subtracting the 35, we get negative 27. So y is equal to 3. And to find the x-coordinate, we substitute it back into here. X is equal to negative 3 times 3 plus 7. So that's negative 9 plus 7, which is negative 2. And then a quick check. 18 minus 10 is in fact 8. Negative 2 plus 9 is in fact 7. Now, in the next video, we're going to look at some of those special cases with parallel lines and coinciding lines, and what that looks like under the method of substitution.